Autonomous drones are reshaping warfare. They're fast, precise, often cheap. You can make them from commercially available parts. They can navigate, surveil, and strike in dangerous zones. And as you heard, they're becoming increasingly autonomous. But they do struggle under uncertainty. Take an example of this autonomous drone that receives a command to hit this target. But before it arrives, unexpected events occur. GPS is spoofed. The target goes missing. Civilians unexpectedly enter the scene. Communications drop, or power goes down. Mission failed. Of course, there are fail-safes, backup batteries, redundant sensors, return-to-home protocols. But at the end of the day, these autonomous systems depend on fragile infrastructure. Power. If power goes down, the drone can fall out of the sky. If the GPS gets spoofed, it can be tricked into navigating in the wrong direction. Communications drop, it's isolated. And as environments become more and more unpredictable, these systems hit computational limits. Power is consumed, they heat up, and they become more easily detectable. So of course, these autonomous drones are highly capable, but they're far from perfect. So the question we ask is, can we make them more adaptive under uncertainty? Can we make them more resilient, and yet remain energy efficient? Nature has solved this problem long ago with the human brain. Nearly 86 billion neurons. No satellite link, no cloud infrastructure, just billions of simple units, sensing, communicating, adapting. And from this network emerges something extraordinary. Racing a mountain bike through unstable terrain, diving into the deep unknown, sprinting through chaos, or even slamming a ball midair. We make split-second decisions under uncertainty. And when one part of our brain fails, the whole system doesn't collapse. It reroutes, it adapts, or if it must, it degrades gracefully. That's resilience. And neural systems were built for exactly the conditions autonomous systems struggle in today. And according to neuroengineers, the brain runs on about 20 watts, what it takes to power an iPhone. Extremely energy efficient. So how does the brain do this? Well, let's first talk about structure. It's this massive 3D parallel network, which enables resilience, right? Because if one part fails, the other part compensates. Children that have debilitating seizures can actually get an entire hemisphere of their brain removed and still grow up to lead normal lives. Resilience. But perhaps the breakthrough about the brain is neuroplasticity, neurochemistry. You see, neurons strengthen and weaken their connections with lived experience, which means they're not fixed systems, they're changing with the environment. They're learning, a child learning a language. They're reorganizing after disruption, a stroke patient relearning how to walk. Machines don't do this, they don't continuously rewire. But there's another really huge advantage about the brain in how it computes information. It's fundamentally what we call event-driven, which means it only spends energy processing information when something meaningfully changes in the environment. So when you put on your clothes in the morning, you first feel them, right, against your skin. Minutes later, you don't even notice. Machines, on the other hand, can sense and process enormous amounts of information every millisecond, right, like a clock, whether that information matters or not. So it's not surprising that we've been spending decades building intelligence by trying to copy the brain, gain these capabilities. But that approach has a ceiling, because copying something is not the same as working with it. What if we could actually work with living neural systems, brain organoids? We interface with them, we observe them, and most importantly, we guide them. That's not science fiction. Labs today, including at Johns Hopkins, the Katoria Lab, are already doing this. DARPA has programs investing in exactly this direction. So the question is no longer, can we? It's how fast. So what is this brain organoid? How do we build it? Well, we start with human stem cells. We apply some chemical signals, gently guide them towards becoming neural cells. These cells find each other. They organize. They form networks, connections, generate electrical activity. And then over weeks, they become these three-dimensional neural structures, living, pulsing, responding brain organoids with multiple brain regions and millions of neurons. Where it gets interesting is that we can actually interface with brain organoids with what we call microelectrode arrays. These are microscopic systems that can sense and stimulate, and they're flexible enough to sit directly against the tissue. So what do? They can record the organoid's activity. They can listen. They can also put controlled inputs, electrical pulses, back into the organoid. They can stimulate, record, stimulate, observe, and guide. This is this bidirectional communication between machine and biology is what everything else I'm going to talk about is based on. But how would you build these systems, though, to become trustworthy? I'm a control systems engineer. And control at its surface is actually quite deceptively simple. We observe a system, we model its behavior, we predict what it's going to do next, and we guide it towards a desirable outcome, this constant feedback loop. But what I want this room to understand is that control theory matters in defense, not just for performance, but for accountability. You see, if systems fail commercially, you lose money. But if systems fail in contested environments, people can die. So control theory provides the mathematical tools that allow us to anticipate failure before it happens and to design robust systems that, if they must fail, they degrade gracefully on our terms. So how would this look like with an organoid system? First, we start with what's called a neuromorphic sensor. This is a system that listens to the organoid's activity and then translates that into the language of machines, position, velocity, decisions. That information is sent to a controller, which compares it according to the mission, the objective we wish the system to achieve. And if the system drifts a little bit from that goal, the controller provides corrective inputs back into the brain organoid. But it does it through a neuromorphic actuator. This is a system that translates the language of the machine back into the language of neurons through carefully, precisely timed electrical pulses. So you might think interface, stimulate a brain organoid. Well, actually, we've been interfacing and stimulating actual human brains clinically for decades. Deep brain stimulation is a therapy to treat Parkinson's disease, epilepsy, and many neurological disorders. And in my lab, we try to close the loop to make these therapies more effective. We sense the brain, compare it to a healthy network. We then let the controller update the stimulation pattern to optimize therapy. So it's not a leap to bring these control principles into guiding brain organoids. Essentially, what we're going to do is we're trying to merge the best of both worlds. We want the precision, the speed, and the capacity to process information of machines. But we want to gain the resilience, the adaptation, and energy efficiency of the living neural system. This is perhaps a new computing paradigm. Not artificial intelligence, but hybrid intelligence. And of course, the future is not one drone. It's swarms. Imagine hundreds, thousands of adaptive systems coordinating, communicating. One swarm is sensing, surveilling. Another swarm is acting on that information. But importantly, the human never leaves the loop. The human can always redirect and, most importantly, override the collective at any moment. So in the future, we're no longer going to deploy fixed systems with preloaded missions. We're going to deploy systems that adapt to the environment, that adapt to adversarial action, that even adapt to their own disruption and damage. And this technology can translate to impact our lives, make self-driving cars more safe, more resilient to changing environments and roads. Autonomous robotics that go into terrains that are inaccessible or too dangerous for humans, underwater vehicles, where the terrain is completely unpredictable. Precision therapeutics. Imagine a set of systems entering the human body, identifying disease, and treating the tumor from within. For decades, we've been trying to build intelligence by copying the brain. But now something new is possible, hybrid intelligence. Machines can become the eyes and ears, sensing enormous amounts of information at scales biology never could. And living neural systems can do what machines lack. They're resilient, they can adapt, and they're extremely energy efficient. So it's like taking two imperfect systems, each compensating for the other limitations. So the future of intelligence is not artificial intelligence alone. It's something that emerges from biology and machine. It's not simply engineered. It's going to be grown, guided, and used responsibly. Thank you.